Okay, so in the previous video we'd made a comparison between C3 conditional inference tree that used the entire HMD Boston Fed dataset, and then that one that excluded
In the previous video clip we were looking at machine learning also and C trees, conditional inference trees. We had run code provided by Halvarian where we had used a C tree to predict whether a mortgage was approved or denied. That model then could be used for predictions, and we had all predictions where we used the complete data set, and then we had no black predict. When we ran that, it gave us these predictions, and then we made a comparison where was the full model where we included all the variables including black, and then all the variables excluding the column for blacks. And we run, and we find that the output from both models is equivalent. Now, does this then allow us to does this then give us license to say is the variable that accounts for race inconsequential? And we might say, well, purely for prediction purposes, yes, but probably this is not evidence that we would say is robust enough that we would be able to exclude race as being an issue here. And then the bigger issue in terms of was there racial discrimination or not, obviously that's a lot more profound. But at first glance it is striking, and it would tend to downplay a little bit the role of race in terms of mortgage origination. There may well be some logic here. Financial institutions might actually be quite happy to lend to people regardless of race, because every loan is generating the potential for additional profit. Okay, so in the next snippet of our script that is provided by Halvarian, he runs the C3 model again. In this instance, he's going to drop not just one of the predictors, but each of them sequentially by using a loop, and then he will investigate the output. Again, the output that you should get from that particular code should be as such. And the way we might interpret this, that if you drop the dir variable, then you predict there's a difference of 2 between the error and all error. So before we had estimated all error. If we recall, all error is this figure of 228 when we ran the C3 on the entire data set. And we generate for each of the C3s, we'll generate 12 C3s. And each time we drop one of the predictors, and going from, so we drop sequentially dir, hir, lvr, and then we compare the level of error for the entire data set against the data set where we have removed sequentially one of the columns as we estimate each C3. Okay, so when we run that output, okay, so maybe to explain, it's a loop, and we drop, so we go from t to 1 to 12. Each time we're dropping the first variable, the second variable, the third variable, all the way up to black, which is the final variable. Then we run that, that then becomes our drop 1, so it's our all data with the excluded variable that becomes drop 1. It's a placeholder. Then we include that, we run deny on that data set that sequentially drops each of the columns one by one. Then we predict from the drop1 fit, and we get the drop1.prd, which is like a prediction. And then we do confusion matrix. So we do, and we estimate the error like what we had done before. We estimate when we ran this before the all confusion, the confusion matrix, we added both of these to get the error for the model. This time we do the same, but we do it for the for each C tree that we've generated where we've removed one of the columns, and we calculate the error for that, and then we compare that error from the reduced data set against the entire data set, and that gives us the all error. So this should be the smallest level of error, and then the error that we have when we drop a variable should be a bit higher, and then we can estimate, do we get 2 additional errors, 0, 6, and so on. So let's run that, see what happens. And the output that we get is consistent with the what's left in the explanation that's provided by HAL. And if we remove dir, we get 2 additional errors. If we remove HIR from the C3, no additional errors. If we remove LVR, we get 6 additional errors. If we remove the credit score, 8 additional errors. If we remove the mortgage credit score, no impact. The public record of bad debt, 12. If we remove denied mortgage insurance, we get 36 additional errors. If we remove the self-employed, no additional errors. Single, no additional errors. Unemployment rate in the occupancy of the applicant, no additional errors. If the individual is buying a condominium or otherwise, no additional errors. And if the individual applicant is black, if we remove that, it doesn't produce for the C3 any additional errors. Okay, so this provides us with, I suppose, a hierarchy of what we might consider as being the most significant factors here. So DMI looks to be very important, PBCR looks to be important, perhaps then credit score, then loan to value ratio, then debt expense to income ratio, debt service to income ratio, and then the more insignificant variables, HIR, self, single, unemployment rate, condo, and black. Okay, so we can compare that then against the Logut model, and we'll do a little bit more in-depth analysis of the Logut model using the style of analysis used in Stock and Watson. But for the moment here, we will just run a confusion. We'll just run a Logut model that includes the entire data set, and then look at the amount of error generated like before. So let's run that. And so this is basically a regression model, but it's binomial, indicating that the ni is a binary, and we're predicting a binary variable, and we're using a Logut logistic regression. Then we will predict the output of this model. So we take the predictions and we create an object called Logut temp, and then so that will produce probability figures, probability outputs, but we would want to convert that then to a 1 or a 0. And if the variable is greater than if the Logut temp is greater than 0.5, then that would go to a 1, otherwise it remains as a 0. Right? And then we can estimate a confusion matrix, and then we can output that, and we can have a look here. Like before, the prediction from the model, false and true. So in other words, when we have on the diagonal here, we have true, and again we have true, and these two variables here, these two cells, when added together produces the overall error of the model. We do have output as well from the logit model, and we have false and true. We could also do logit temp, and if we look at logit temp, it should give us a probability. So logit temp, if we run that, let's just investigate that, and you can see we're getting probability measures. And to convert that logit temp to actual false or true, then we use this 0.5. If the probability is greater than 0.5, yes, denied. Otherwise, no, mortgage approved. Okay, when we estimate the total error here and output that, we have a value of 225. And interestingly, that is better than the C-tree model that uses the entire data set. So the C-tree, the best C-tree model that included all the entire data set, gave us an error of 228, which was higher than the logit model. So the logit model seems to be performing quite well here. When we run the summary logit fit, that'll give us the coefficients of the model and the z or the t statistics and the p-values. And again, this is another way perhaps of investigating which variables are probably somewhat significant. So DIR is statistically significant, LVR is statistically significant, the credit score is statistically significant, the mortgage credit score just outside, right? So not the p-value here is greater than 0.05, so not statistically significant. The public record of a bad debt against the individual, that's statistically significant. DMI, yes, highly statistically significant, so they tend to be greater than 2. If the individual is buying a condominium, had bore no relationship here. And when we look at the race of the applicant, it also is statistically significant, and the p-value is very, very low, which tends to support the hypothesis that the variable for race is important as an explanatory variable. So that's something to note. Now in the next video, we'll turn to random forests and we'll continue this analysis provided by Hal Varian, and we'll compare the 3 different types of models and explore the differences and the different predictions by each of the respective models.